In the last session, I compared the field patterns inside a cylindrical waveguide with that in rectangular waveguide. And we more or less understand that the circular surface of the cylindrical waveguide will concentrate the field on the axis. So the field cannot be described by a simple sine or cosine functions like those we use for the rectangular waveguide. So in this session, I'm going to introduce new mathematical functions to properly describe the field inside a cylindrical waveguide. So previously, we already have a solution for the field along the phi direction, along the angular direction, but we haven't really solved the field along r direction. And from the separation of variable technique, we write down this expression from the Helmholtz equation. So now we are in the position to solve r from this ordinary differential equation. But don't forget that the n is the mole number along phi direction. And I want to record some material from lecture 10 in electromagnetic 1. In fact, this is the solution belong to a family of spatial functions called Bessel functions. So if you still remember, we can write down the solution of this expression, this ordinary differential equation, with this form, which is a superposition of Bessel function of the first kind and second kind with some argument here, hr, and h is the eigenvalue in the Helmholtz equation. And of course, this value has to be decided from the boundary conditions. And the Bessel function of the second kind is also called Newman function. If we allow this argument hr to increase to a big value, then it's easier to understand how this Bessel function will vary with r. For example, if we allow the argument of this Bessel function of the first kind of order n to go to a large value for this argument nu to go to a large value, then asymptotically this Bessel function is going to very much like a cosine function. So you can sort of get the idea that this Bessel function is very similar to a cosine-like solution, and with a larger argument, you have periodical variation inside it. Similarly, if you allow the argument of this Newman function to increase to a large value, then the Newman function is going to behave very much like a sinusoidal function. So when you write down this the Bessel function of the first kind and second kind, bear in mind that the solution is very much like a sinusoidal function. So we can use this Bessel function to describe the field inside a cylindrical waveguide. Now, let me just plot the J versus the x on this diagram. For J0, which is the Bessel function of the first kind of order 0, it varies like this. So at the beginning, there's a large value on the axis, and then it starts to oscillate along x direction. For large x, all the Bessel function of the first kind will just approach sinusoidal function. This second curve here is J1, and this third curve, yellow curve, is J2. And quite often, we want to understand the zero crossings of those functions on the x-axis, and we call this the zeros of Jn of x. The location where Jn of x will be crossing the zero line is called the zeros of Jn of x. For example, now everybody please follow me to look into this blue curve, which is J0. The first zero crossing is right at this point. And this value, this x value is equal to 2.405. So this 2.405 is labeled on this chart. And this n equal to 0 means we are looking into GA0 Bessel function. And this 1 tells you the first zero crossing for this GA0 function. And for the second zero crossing, it's going to happen at this point. So this x02 is equal to 5.520. And we can also look into the zero crossings for different curves on this diagram. For example, if we now pay our attention to this GA1 curve right here, the first zero crossing for the GA1 curve is going to be at 3.832, and we label this as x11 right at this location of this chart. N equal to 1 and p equal to 1, and n is the mole number in phi direction, and this 1 is the first zero crossing for this GA1 function. So we can also identify, for example, the second zero crossing for the GA1 function right at this point. And so x12 now is equal to 7.016. And sometimes we are interested in the zero crossing of the derivative of Bessel functions. So for example, if we pay our attention to this value, this means that we are looking into the zero crossing of the derivative of GA0 function, and we pay our attention to the first zero crossing point 1. So for example, this point happened to be also the zero crossing of the derivative of the GA0 function, because well, now you just follow me with this blue curve. And if the derivative of this function will go to 0, this means that the slope of this curve will go to 0. And you can identify that this point is going to be the first zero crossing point for the derivative of GA0x, because the slope of this curve at this point is going to be equal to 0. And this match to this point. So this 3.832 location is also the first zero crossing point for GA0 function. And so I also label this point as the x prime 01 because this is the first zero crossing point of this GA0 function. Well, similarly, you can also identify the second zero crossing point for the derivative of GA0 function, because the second point where you have a zero slope is this point on this GA0 function. So at this point, I also label it as x prime 02 equal to 7.016. And quite often that we are interested in the zero crossing point closest to this vertical axis. So if you compare those zero crossing points for the derivative of the Bessel functions, you can tell that this point where you have a zero slope is going to be the point closest to this vertical axis. And this point is labeled as x prime 11 equal to 1.846, because this point is on GA1 curve. So the first label 1 means that we are looking into the GA1 curve, and the second index 1 tells you that this is the first zero crossing point on this GA1 prime curve. So this is the important that you identify those zero crossing point, because later on we'll be using Bessel functions to match to the boundary conditions. And on the boundary, the tangential component of the electric field has to go to 0. So the zero crossing points are quite often matched to the boundaries of a cylindrical waveguide. Now, let's turn our attention to the Bessel function of the second kind, which is also one of the standard wave solutions which is described. And this curve has been shown also in lecture 10 in electromagnetic 1 when we deal with the Laplace equation for electric potential. The characteristic of this Newman function is that you get a value diverged at x equal to 0. So if you deal with a problem where r equal to 0 is involved, you should avoid using this Newman function as a solution. But quite often that we use the coaxial cable as a cylindrical waveguide for guiding electromagnetic signal. And in this cylindrical waveguide, you don't involve the solution at r equal to 0. So quite often that we pick up Newman function as a solution for a coaxial waveguide. And sometimes we don't just want to get standing wave solutions. Sometimes we want to look into the field outside waveguide, which is evanescent. For example, in the optical fiber, which is a dielectric waveguide, you have wave guided inside, but you will have the evanescent wave outside. Then for such a situation, the eigenvalue will be imaginary number. So if you put this imaginary number into sinusoidal-like solutions, you're going to get solutions similar to Kash function, Sinch function, or exponential function with the real exponent. So same thing happened to the solutions inside a cylindrical waveguide. If you put the argument of the Bessel function of first kind and second kind with the imaginary number, then you turn the Bessel functions into modified Bessel function. And for example, if I have the modified Bessel function of the first kind and allow this argument approach a big value, then this function is going to approach an exponential function like this. Plot here is the I0 nu, which is the modified Bessel function of the first kind of order 0. You can see that the value of this modified Bessel function will increase with nu when nu increased to a big number. On the other hand, if we allow this argument of the modified Bessel function of the second kind to be large, then you will also create such an asymptotic form, which is the attenuating exponential function. And this is a solution that will be adopted for an evanescent wave. For example, if you have an optical fiber and the wave is guided inside, but the wave outside the optical fiber is going to be an evanescent wave, then the field is going to be described by this modified Bessel function of the second kind, and this n again is a mole number along the phi direction. And sometimes you want to deal with the problem involving r equal to 0. Then you have to be careful about this situation where this k modified Bessel function diverge at r equal to 0. So you deal with a field involving r equal to 0, then you cannot pick up this k as your solution. And in some situation, you have a radiation wave outside a cylindrical structure. So we still need to find a proper solution to describe the field radiating away from the cylindrical structure. And now, if you do a superposition of the Bessel function j and n and put an imaginary unit before it, then you can construct a radiation wave from such a superposition. So again, if you allow this HR approach a big value, then this is nothing more than a complex exponential describing a wave radiating along r direction, and we call this Hankel function. And so if you want to describe a radiation wave, then you have to involve a Hankel function in your solution. And the cartoon shows you the scenario where you want to use this solution. For example, if you have a waveguide, and it could be a waveguide with some leaking field like this, and the radiation just leak away from this waveguide. Then this part of the field and this part of the field will be described by Hankel function. On the other hand, if this is the antenna structure, and you excite some current wave on this antenna, then the field radiating away from the surface of this antenna is also described by Hankel function, because Hankel function is the mathematical expression describing a field radiating away from a cylindrical structure. And you can see 1 over r, 1 over square root of r dependence in this expression, because the energy density is going to reduce along the radial direction. So in this session, I introduced quite a few mathematical expressions. 那它们都是在一个家族里头叫做 Bessel function。所以呢，这个在 r 的方向上头呢，我们是用 Bessel function 来描述一个圆柱状波导里头的场的这个变化。那所以譬如说，我们如果是用 Bessel function of the first and second kind， 那我们就是在描述这个圆柱状波导里头的驻波沿着 r 的方向，就是这个径向的这个变化。它们呢就像这个 sin 或 cosine 类似的这个解，只是呢在这个这个 axis 上头，就是轴上的它的这个 Bessel function 可以告诉你说它的场是比较大的。那 modified Bessel function 呢是用来描述 evanescent wave 或 surface wave。因为呢，它的这个场呢不是上下震荡，而是一个类似 exponential decay 或 exponential growth 的这么一个dependence。那 Hankel function 呢，也是这个 Bessel function 里头的一个家族成员。那它是来自这个 Bessel function first kind 跟 second kind 的 superposition， 只是在这个里头呢加进了这个虚数单位到里头去。那它可以适当的描述一个辐射的这个场沿着这个 r 的方向。那这个场的描述呢，对于这个天线的辐射就相当有帮助，因为通常一根天线的话，就是一个圆柱的系统的一个器件。所以这是我们这个小节里头学到的一些数学的常识。